let's do some exact DEs. First thing we got to do is check and see if these are exact. And I picked out some problems to do this morning and kind of did these in my head, and I think they're all going to be exact. But if one of these turns out to not be exact, then hey, that's a great non-example. I think I can make space here and do these separately. Okay, so we got this DE here in differential form. This thing in front of dx there we call capital M, and this thing here in front of dy we call capital N. The DE is exact if and only if partial of M with respect to y is the same as the partial of N with respect to x. That was a bad partial symbol there. Exact if. So we have to check that. If it's not exact, the Shams outline does show you a trick to use using integrating factors. For DEs that are not exact, you can convert them into an exact DE sometimes. Like they go through 2 or 3 examples, and then there are a couple of homework questions where the method they give in the book doesn't work, and the answer in the back of the book is wrong. So in my experience, that just caused too much confusion. I don't even deal with that. So at this point, if the DE is not exact, we just go, oh, well, we don't know how to do with it. So if we turn out this guy, if it turns out to be no, it's not exact, we're done with it. Let's check. So this guy here, we want the derivative with respect to y. We're treating x as a constant. So partial M partial y. Derivative of y with respect to y would be 1. Derivative of x, and that's just a constant. That'll just come along for the ride. Same with the 2. Derivative of y cubed will be 3y squared. So we'll get 6x y squared. So the 2 and the x came along for the ride, and that 3 got multiplied down. Partial N with respect to x, derivative of 1 is 0. Derivative of x will be 1 with respect to x. And here, the 3 and the y squared just come along for the ride. Derivative of x squared would be 2x, so we'll get 2 times 3. We'll get a 6x. The y squared comes along for the ride, and then plus 1. Partial x with respect to x is 1. Those are the same. So this guy is an exact DE. What's that mean, is exact? That means that it is the exact full differential of some higher dimensional function. That means the left-hand side is the full differential for some function that depends on both x and y. That's who we need to find. That's our goal. And there are 2 different ways to approach this. You can do 2 different integrals and compare, or you can integrate and then differentiate with respect to the other variable and compare. You can do 2 integrals or an integral and a derivative. Either way's fine. Some of the videos in the homework will do the second way. Some will do the first way. It's up to you. I like the first way. And so the way I approach these is this function f must be the antiderivative of m dx. Notice here, by the way, when I was doing the partial, m is sitting beside dx. M is all the stuff in front of dx. When I was comparing partials, I used the wrong variable. He's beside dx. I took his derivative with respect to y. When I'm integrating, I'm using the right variable. He's beside dx, I'm integrating him with respect to dx. Okay, so antiderivative of y dx would be yx, because y is just a constant, plus antiderivative of the y cubed, those are just constants. They come along for the ride. Antiderivative of x dx is x squared over 2. That'll cancel that guy. So we'll get x squared y cubed. Plus, here's the important part. Plus, potentially, maybe f had some extra y's in it. And when I took the partials with respect to x, those y's disappeared. So there could potentially, I think I typically use g here. Doesn't matter. I could call this whatever I want. There could potentially be some extra function of y that didn't pop up from this. So that's one way to find f. The other is it could be the antiderivative of n with respect to y. So let's take his antiderivative with respect to y. We're going to get antiderivative of 1 is y. Plus antiderivative of all this stuff, I'm going to get a y cubed over 3. That'll cancel that 3. X squared y cubed. Plus antiderivative of x with respect to y would be xy. Plus, again, possibly some function of x. Remember, we're thinking about this entire left-hand side is the full differential. We had some f. I'm going to erase all this in a minute. We've got some f, some function that's got x's and y's in it. And I'm claiming that if I do this thing, the differential, which by definition is the partial of f with respect to x dx plus the partial with respect to y dy. Remember, in higher dimensions, we don't use the derivative. You guys will probably never in your life see the full derivative of a 2-variable function. The full derivative is a matrix. It's not a formula. You have the gradient, you've got the divergence, you've got the curl, you've got the differential. Yet we have all these differential operators. They're not the derivative. This is the closest thing we have that you've actually seen to what we might call like a derivative, and it's called the differential. You learned this in Calc 3. So the full differential of some function by definition is this. We are saying that that's this right here, that this guy right here is m, and this guy right here is what we called n. So that's saying that m is the partial derivative of this guy we're looking for with respect to x, and same for n with respect to y. So that means that if f here had something in it that only had y's in it, say f here had a bunch of stuff and at the end it had a 3y. Well, then if I take his partial with respect to x, that's just 0. That 3y there is not going to affect this guy at all. It won't show up there because he doesn't depend, that thing there doesn't depend on x. So if there's anything in the formula that only has y's in it, it won't show up in m. Similarly, if there's anything in here that only has x's in it, if there is an x squared over 5, that won't show up in n. These are the guys we got to try to find. Okay. So we did the integral both ways, one with respect to x, one with respect to y, and now we compare. A lot of times you'll get exactly the same thing and then you're done. Other times you'll just get some repeats with some extra stuff. So this function f, we write down anything that's repeated. I see, oh, I have to have an x squared y cubed. That's in both. Both of them have an xy. And now I want to look here and say, okay, was there some extra function that only depended on y that I missed here? Yeah, there was. Look, it's right there. There's that extra function of y. It was just y. Was there some extra function of x that didn't show up here that maybe I picked up there? No, there's nothing extra. I've counted everything. So that guy there was just 0. So there's that function I was looking for. So I've got f. I'm not done. That's not the solution to the DE. The original DE up here said that the differential of f must equal 0. Remember, that's what the left-hand side here is. That's the full differential. And that equals 0. The only way the full differential can equal 0 is if the function is equal to a constant. So the solution is that capital F equals a constant, x squared y cubed plus xy plus y equals a constant. That's the solution curve to the DE. 99% of the time, we're going to have to leave this in implicit form. We can't solve it and get y equals stuff, because these usually will not be functions. They'll be curves in space. So that's the solution. But I want to point out something to you here. In the homework, most of the time, they don't want you to write this line. They want you to just stop here and just give that. So let's take a look at this in the homework. Like here's one right here. They're saying, look, we know the solution is going to be whatever you get equals C. That's the solution. Don't write all that. Just tell me what you got for F. So in this homework problem, for example, you would just type in this. Okay, let's do another one, but I'll go through it a little quicker. Let's check and see if this guy is exact. So partial m with respect to y. Let's see, we're going to get an x. That's it. His partial with respect to y is x. Partial n with respect to x is going to be y. His derivative is 0, his derivative is 0. Those aren't the same. Those are not equal, not exact. We're done. Maybe we could solve this a different way. Maybe we could solve it as a separable DE. Maybe it's a linear DE. We might have other methods, but this method that we did here won't work on that one because it's not exact. Okay, what about this one? So here, we got to be careful here because now they've changed our variables up on us. We're using t and x. So if we call this guy m and this guy n, we want the partial of m with respect to the other variable, not the guy sitting beside him. So let's see, that would be 2x. And partial n respect to the other variable t would also be 2x. Remember, the derivative of x with respect to t is x is a constant as far as t is concerned. That would be 0. because we're doing partials here. Those are the same. So this guy is exact. So then I can couple that a little bit. Capital F, maybe I'll do this one the other way. I'll use the other method. Capital F must be the antiderivative of M with respect to the variable he uses, dt. So that would be antiderivative t squared plus x squared dt. That would be t cubed over 3 plus x squared t, plus possibly some extra function of the other guy. Okay, everybody with me? If you have any questions, feel free to yell out and stop me. Okay. And then again, the way I would do this is say, okay, F must also be the antiderivative of the second one with respect to the other variable. So that would be antiderivative 2tx minus x dx, which would be, let's see, we get an x squared over 2. That would cancel that 2. That would be t squared x squared minus antiderivative of x would be x squared over 2. Okay, so we found that guy. Plus possibly some extra function of y that we would need, or not y. You get used to writing y's, don't you? T. Maybe some extra function of t that only showed up here. Yeah, there is. Look, he's right there. So now we just grab everything that's common, like wait, am I missing something here? Yeah, that shouldn't be a squared there, right? Where's my, sorry, my thing's in the way. Right there. Antiderivative of 2tx with respect to x, the t just comes along for the right there. I wrote a squared there and there shouldn't have been a squared. These guys are the same. I'm still erasing. So you keep anything that's the same and then you write down anybody that's only in one. You don't write anything down twice. So capital F would be x squared t plus t cubed over 3. There's that extra function of t I was looking for, plus negative x squared over 2. There's that extra function of x I was looking for. And then we set that guy equal to c, and that's our solution. Okay, so the other method I was going to show you was get here. So pretend I did not do this chunk here. Get F, and then say, well, N is supposed to be the partial of F with respect to X. So now we're going to see, we integrated that with respect to T. Now we're going to take the derivative with respect to X. So the derivative of that thing right there with respect to X would be 0. Derivative of this guy with respect to X would be 2xt plus some G prime of X. And what's that supposed to equal? What was N? N was this. So that's supposed to be 2tx minus x. So look, those match. That means G prime must be negative x. So we just integrate both sides, dx. and get G, that thing we were looking for. That's just chain rule there, the antiderivative of the derivative. That's a fundamental theorem of calculus. That's just G. Antiderivative of negative x would be negative x squared over 2. We found it. We found that extra function of G, or that extra function of x. So we just tack it on there. I don't like that method. Again, if you watch some of the extra videos I put in the homework, you'll find some people that do it that way. You got to integrate, then differentiate, then integrate with respect to all kinds of different variables. I think it leads to confusion. I like this way better. Integrate M with the right guy, integrate N with the right guy, match up stuff, keep everything you see. Anything that's repeated, don't write it twice. What you cannot do, what I see people do all the time and is wrong, is this. Like on a test, you will not get credit for this because it's just wrong. They just do this. Sometimes they'll write a differential over here, sometimes they won't. They'll just start integrating everything. And let's say we did that. Let's do it. Let's integrate this thing here with respect to t. What would I get? That would be t cubed over 3 plus x squared t. Plus, now integrate this thing with respect to x. I'm going to get an x squared over 2. I'm going to get a t x squared minus x squared over 2. I don't know, maybe this was dx. Most of the time, they don't even bother to write a differential when they do this, but say they at least bothered. Antiderivative of 0 is some constant. But now look what happened. These are the same thing. I end up with this as my solution. Anything that was repeated, anything that came in both, we've now counted twice. Because I had it from that one and that one. And that's just wrong. That's not the right answer. That's not the solution to this DE. Say, look, I didn't have 2 of these, I only had 1. And mathematically, you can't do that. You can't just start throwing integrals around and integrating everything. That is the wrong approach. But it's a very common mistake people make.
Hey, Professor.
Yeah.
I have a question. I'm sorry. Can you go back up really quick to the beginning part of the solution? I'm sorry. Just asking, when we do the derivative of dn to the dt for the first part to make them exact,
we're not making it exact. We're checking to see.
Oh, we're checking if it's exact. I'm sorry. We're checking if it's exact. Are we taking the derivative to the partial of t, so this would equal 2x? Or we're taking it to t? I'm sorry. I'm just over confusing myself. I always sometimes overthink it. I know we're taking this.
Yeah, you're overthinking it. We're taking, see how he has a dx beside him?
Yes, sir.
We're taking his partial with the other one. Whatever's sitting here, we use the other one.
Okay.
Taking this guy's partial with respect to t and checking to see if we get the same thing as when we do this guy's partial with respect to x.
Okay, so this is supposed to be 2t, right? It's supposed to be 2t, or is that supposed to be 2x?
No, that's 2x.
Oh, okay, 2x. I'm sorry.
Right, so I've got 2tx, and if I want his partial with respect to t, the x just comes along for the ride.
Oh.
The 2 just comes along for the ride. Derivative of t with respect to t is just 1.
Just 1, yeah.
So you just get 2x.
Gotcha. Sorry, I'm overthinking it.
It happens. Okay, I want to do one more. I'm going to end with the easiest one because I can get a lot of mileage out of this problem. First off, this is exact. So here's m, here's n. Partial m with respect to the wrong guy. Why? is 1. Derivative of y with respect to y is 1. Partial n respect to x, the wrong guy. Derivative of x with respect to x is 1. Those are equal. This guy is exact. So I can solve this as an exact DE. I can say, well, then the DE is the full differential for some f such that m is partial f with respect to x and n is partial f with respect to y. Notice now I'm using the correct one. M is beside x, n is beside y. So f must be the antiderivative of m dx, antiderivative of y dx is just yx or xy, plus possibly some extra function of y that we didn't get. Maybe we'll pick it up here. We won't. It's also the antiderivative of n dy. So antiderivative of the thing in front of dy, that's just xy, plus maybe there was some other function of x that just didn't show up in n. We can see there aren't. There's nothing. We just get f of xy equals, just write down everything that's common, xy. So the solution to the DE is xy equals c. We could even write that in explicit form if we wanted. I could say y equals c over x. Okay, I solved that as an exact DE. This guy's also separable. So my DE was, what was it, y dx plus x dy equals 0. This is separable. It doesn't look separable right now. Separable usually means in differential form, everybody right here is x's and everybody right here is y's. But if I divide everything by xy, I could get it like that. Or if I put this in standard form, so let's move that dy over, or I'm going to move things around a little bit. I'm going to write x dy equals negative y dx. I move this term to the other side. I'm going to move all my y's to the left side, all my x's to the right side. That's multiplied. So I can't add and subtract that y over. I have to multiply or divide it. Same with that x. So I could divide this over and get 1 over y dy. Divide that x over, negative 1 over x dx. I've separated my variables. So I can just integrate both sides. Technically, again, I've mentioned this before, we're really integrating both sides with respect to x, but by chain rule, dy dx dx is dy. We're integrating this side with respect to y and this side with respect to x, and we get natural log of the absolute value of y equals negative natural log absolute value of x. Now, I want you to watch what happens here, because here's a common mistake people make. A lot of times people like to wait until the end before they put in their plus c. So I'm going to make a mistake here on purpose, and then I'm going to come back and fix it. I'm going to say, I'm going to wait until the end, and I'll put the plus c in at the end when I'm done. And you'll see we get the wrong answer. Okay, so for simplicity, let's assume everybody is positive. That is the worst assume ever. I mean, first off, I had them in the bottom. Neither one's allowed to be 0. So we've got a discontinuity here anyways. We'll take what we call the positive branch. So I can drop these absolute values. Okay, rules of logs say I can bring that negative up inside here and get ln of y equals ln of x to the -1. That's just ln of 1 over x. Then I can make both sides powers of e and get y equals 1 over x. Because e raised to the ln, those cancel out. Oh, I forgot about my plus c. I'll just throw it in at the end. Look at that solution. 1 over x plus c versus c divided by x. Those are not the same. Let me make this smaller so you can see them both at once. Those are not the same. You cannot wait until the very end and just go, oh, I'll tack in my plus c now. This is wrong. You have to put the plus c right here. When you do the integral, that's when the plus c has to go on one side or the other. It doesn't matter. Okay, so let's do this the correct way. Plus c. So now I'm going to play the same kind of game. Let's drop the absolute value so I don't have to worry about that. I'm going to bring in that -1. This is still going to be a 1 over x plus c. Make both sides powers of e. E raised to the ln of y would just be y. Over here, e raised to this stuff, I could think of this as e to the ln of 1 over x times e to the c. E to the ln, those cancel out. E to the c here, well, that's really just another constant. I'm just going to call that some new c. Now that c right there and that c right there are different c's. So sometimes, back when I took this class, I was so meticulous about this. I would go, well, I'm going to call this C1. Right there, that's C1, and that's really a new C. That's, let's say here, C2 is e to the C1. And I'm going to show you right now that you don't have to stress about that. It doesn't matter. Just call it C. And I'll show you why and where it matters. So we could do that, but I'm not going to. I'm just going to go, nah. How you spell nah? Is that how you spell? Like if you go, nah. Anybody know?
I think that would be the correct spelling.
I'm going to go with it. Nah. We'll just say y equals 1 over x times c. Or c over x. That's the same solution we got here, by the way. Look at that. Same solution. So first off, we could solve this dE as an exact dE, or we could solve it as separable. It's also linear. We could, let me make sure that's true. This may not be linear. Because if we put it in dy dx, yeah, if we put it in standard form, it would be a linear dE. So we can solve it using an integrating factor. There are a bunch of different ways. I don't want you to get in your head that dEs are one type or the other. They might be multiple types. They might be none of them. There might be multiple different ways you can solve. And I also want to emphasize that when you're solving a particular solution, an initial value problem, that's the only time you got to worry about these different constants. So I'm going to write up two different things here. Let's solve an IVP. Y of 1 equals 1. So I had two different versions of my solution. We had ln of y equals ln of 1 over x plus c1. And we had, let's call that version 1. And we had y equals c2 over x. Let's call that version 2. If I go to solve this IVP, absolutely, I'm going to get different answers for C1 and C2. Absolutely. There's no doubt about that. Let's do it. So using version 1, if I plug in a 1 for x and a 1 for y, I'll get natural log of 1 equals ln of 1 over 1 plus C1. Natural log of 1 is 0. 0 equals 0 plus C1. So C1 equals 0. My particular solution would be ln of y equals ln of 1 over x. That's the solution. Let's write that in explicit form. That's implicit form because y is not isolated. Just make both sides powers of e, and you get y equals 1 over x. So that was implicit. This is explicit. Okay, now let's do the same thing using version 2. So I had y equals c2 over x, subject to y of 1 equals 1. So just plug in an x of 1. Remember, that's your x. That's your y. I get 1 equals c2 over 1. C2 equals 1. Completely different than what I got up here. Look at that. Not the same. Different. However, plug it in. What's my solution? Plug in C2 equals 1. I still get y equals 1 over x. I still get the same answer. So it doesn't matter. I don't have to go through the trouble of saying, well, that's C1 and that's C2. You might have a problem where you keep changing C 17 different times. 2 times C, it's just a new C. E to the C, just a new C. C squared, it's a constant squared, it's a new constant. You don't have to stress about that and keep track of all the C's. Get to where you're comfortable stopping and just stop there and call it C. What may differ, though, is if one person stops here and somebody else stops here and you solve an initial value problem, you're going to disagree on the C's. So you and your group mate, maybe Bob solved the problem and they stopped here and they just had plus C and you wrote this, you're going to disagree on the constant. But if you put both answers in like your final form, they're going to agree. You still both got the same final answer. You just disagreed on this number. Does that make sense to everyone? I hope so. At the end of the day, you still get the exact same particular solution. So it's just something you got to look out for. Okay. Any questions about any of this?
It was basically the same answer, just written in 2 formats.
Yes.
Gotcha.
So the question is, could I solve y prime equals x over y? X over y, yeah, I think that would be exact. Let's say that the question is y prime equals x over y. I mean, that's definitely separable. That's y dy equals x dx. Yeah, that's exact. Because if I put it in differential form, his partial with respect to y is 0. His partial with respect to x is 0. That's exact. That's separable. It's linear. It's all of them. And it's really easy to solve. Just integrate both sides. We get y squared over 2 equals x squared over 2 plus c. There's this general solution, which again, it's a hyperbola. This would be y squared over 2 minus x squared over 2 equals c. There's a chat. Right, just because we've written something in a form that's not exact doesn't mean we can't convert it to exact. So the question is, well, what if I write it like this? In that form, no, that's not exact. If I multiply everybody by y, I could make it exact. Now we could get into the argument of, well, do these have the same solution set then? Because here I'm definitely not allowed to have y equals 0. You can't divide by 0, whereas here I can. If y equals 0, we're not allowed to multiply both sides by it. You're not allowed to multiply both sides by an equation by y. So we really, if I'm going to make this kind of jump, I really should put a disclaimer here. Y is not allowed to be 0. But I don't think y equals 0 is even part, like I think this is a hyperbola. I may have it backwards, but I think it's going to look like this. So that y equals 0 is never in the solution set to begin with. So we wouldn't have to worry about it there. So the question is, can you try other ways to force things to be exact? Absolutely. Of course. Now, I wouldn't do much. Like I said, the Shum outline goes through some problems that aren't that easily convertible. Like that one there, I easily made it exact. Here's one, like this one. They show you how to use what's called an integrating factor to go through a whole lot of work to convert something to an exact DE. And like maybe in the new edition, they fixed the problem, but there was in the old edition, at least in the 4th edition, I think, there was a problem in the down here in the suggested problems. I don't remember which one. Maybe it was this one. I can't remember. But there was one in the solution set at the end. They used that same technique to try to force it to be exact using an integrating factor. And they got the wrong answer. Something went wrong. And like all of us, we spent a whole class period on this once in a face-to-face class, and we couldn't even figure out what they did wrong. So my point is, there are other times when you can go through a whole lot of work to make something exact. Don't expect to ever do that in this class. I wouldn't ask you to do any of that. In fact, like on a test, it's either already going to be exact or it's not. You won't have to do any work at all. Okay, other questions?